Would you like to be able to see into the future? That is an intriguing question that has been contemplated time and time again throughout human history. Famous stories from the Oracle of Delphi all the way to the hysteria around the Mayan calendar in modern times have in some way dealt with the idea of humans seeing into the future. This idea has shaped popular culture and our science fiction with that one tantalizing idea of what if. In the real world, the answer to the question of can we see into the future has been answered with a resounding no. In our ever-evolving society, the trend today is to look toward the future by relying on predictive modeling to best predict the probability of an outcome. But we all know that even these well-thought-out predictions based on data often turn out to be not so predictable. Although it's clear that future events remain virtually unknowable, there is one group within NASA that comes as close as you can to seeing into the future. Throughout NASA's field centers, members of the Fixed Wing Project team are peering into the future every day and coming up with concepts that they believe will be on the next generation of aircraft. Because it takes years to plan and develop these concepts, the hardware and theories that are being tested today will be key components that enable the next generation of aircraft to take flight. On this episode of NASA X, follow us around the country as we visit members of the Fundamental Aeronautics Program's Fixed Wing Project, who are developing the framework that will shape how aircraft of the future will fly. Take a look behind the gates of NASA to see what some of these new ideas look like and how the engineers of NASA are paving the way for the ideas that will change the future of flight. To the untrained eye, most of the aircraft of today look very similar. This is because over the past century of flight, aeronautical engineers have worked hard to optimize passenger aircraft to the point where they are as efficient and safe as possible. As a result, the basic tube and wing shape has been configured and examined from every possible angle, making it the most efficient design possible today. Although aircraft have looked basically the same over the past few decades, if you look closely, you can see some of the major design changes. Wings that were once swept back more dramatically now are less so because of advances in aerodynamic shaping. Engines that spewed emissions by the ton are now much more efficient. Materials that were once so heavy that they significantly weighed down a craft are now much lighter and stronger. With all this improvement and efficiency, it is fair to ask if there is anything else that can be done to make flight even better. The answer is of course yes. Behind the gates of NASA, there are scores of researchers who know that we can still make aircraft better because they are working toward these long-term goals every day. Some of these researchers from the Fixed Wing Project are working on so-called N+3 configurations and goals. In mathematical terms, the letter N is where you start now. N+1 is the next step. N+2 is just beyond that, and so on. Here in the Fixed Wing Project, N+3 equates to aircraft that will be flying in around the 2030-2035 timeframe. For this team, everything is on the table, including engines, fuels, wings, and fuselage shapes.
Well, we need to remember the first A in NASA is aeronautics. So it's a National Aeronautics and Space Administration. Aeronautics is the field of research for airplanes. The airplanes that will fly today were researched and experimented within NASA many years ago. So we're trying to continue that tradition, that important work that we have done for the nation and the world for 20, 30 years from now. Fixed Wing is a NASA research program in where we are doing activities to try to improve the airplanes that we're going to be flying in the future. We're trying to make them less noisy. We're trying to make them better for the environment. We're trying to make them in a fashion that they will use less fuel.
The research we're doing is important because air travel it's such an important part of your life. People travel, even if you don't travel, cargo gets carried every single day. You use something every single day that gets carried by an aircraft. It's part of our way of life these days, and it often gets taken for granted. There are challenges though, so we are focused on exploring and developing technologies and concepts to improve the energy efficiency and environmental compatibility of transport aircraft.
With this mandate to significantly lower noise and emissions and increase performance for subsonic aircraft, there will be a need to address virtually every aspect of the current aircraft configuration, including developing new materials and engines, testing alternative fuels, and even changing the fundamental shape of the aircraft. All across the country, fixed-wing researchers are doing just that. Major advancements are being made into the understanding of how future aircraft will fly. Because there are so many areas of study, let's first look at something that has the potential to be used today as well as in the 2030 timeframe: alternative fuels. On this beautiful morning at NASA Dryden in California's high desert, a test called ACCESS, or the Alternative Fuel Effects on Contrails and Cruise Emissions test, was performed to study the effects of alternate biofuel on engine performance, emissions, and aircraft-generated contrails at altitude. For this test, 2 aircraft were flown in tandem. The first is NASA's DC-8, which will be burning an alternative fuel. The second aircraft is NASA's Falcon that will fly directly behind the DC-8 to measure and characterize the emissions coming out of the engines from the alternative fuel. Here is NASA's Bruce Anderson to explain.
NASA's role is in assessing the combustion characteristics of alternative fuels, as well as determining how these fuels will affect the performance and emissions from aircraft. To understand how aircraft affect the climate, we need to make measurements at cruise altitudes. So the focus of ACCESS, or the alternative fuel effects on contrails and cruise emissions, was to fly behind the DC-8 in flight and look at its emission and contrail characteristics as we changed from standard jet fuel to a fuel that was a blend of a fuel that was made from camelina plant oil, and also added 50% of Jet A to that. There are some other groups out there. Tyson Foods is making a biodiesel and biojet fuel from chicken fat that they sweep up on their processing plant floors. So there's a number of different ways of making these alternative fuels. All of them result in a fairly clean kerosene that doesn't have nearly the contaminants in it that the fuels from refineries do. The fundamental thing is the aircraft has to retain its performance characteristics when you burn a fuel. You can't have any drop in power. The fuel also has to have similar characteristics in terms of density and volume to kerosene. So what we're looking at is drop-in fuels. A lot of the fuel systems on the aircraft are designed to rely on the aromatics in the fossil fuels to swell the seals to make them leak tight. So when we fly an alternative fuel, we have to mix it with standard fuel to retain those properties. Otherwise, the fuel would just leak out of the aircraft. And then the second thing we're looking at is just the emission characteristics. By that I mean the amount of pollutant generated per kilogram of fuel burn.
After the first few flights, it was shown that using these types of alternative fuels could significantly reduce emissions at cruise altitudes, particularly soot emissions. Work continues to better understand how to use these fuels and how to make them even more efficient for future aircraft. Other than alternative fuels, there are some other ideas out there for finding more efficient ways to power aircraft. If we look on our roads today, many of the cars that are now being driven run on a combination of fuel and electricity. The idea that aircraft could do this seemed far-fetched only a few short years ago, but today, this idea is gaining traction. There are several ideas on how to do this, so let's take a look at a few. Here, a team is looking over a new Boeing aircraft design called Sugar Volt. This unique design has several interesting changes, like the truss-braced wings that have the potential to reduce the drag of the wings by making them longer and thinner. Because thin, long wings have the tendency to flex more, designers have included a clever, efficient truss structure to support them. This design has the potential to reduce drag and weight, thereby making the craft more efficient to operate. At first glance, those unique structural changes may look like the biggest game changer for this type of aircraft, but the Sugar concept holds another surprise as well.
In the case of the Sugar concept, what's less obvious to the eye when you see it is that it has an unconventional propulsion system. It's a hybrid gas-electric concept that's closer to what you see in a Prius. It has batteries and a gas turbine engine technology. It requires advances to battery technology, but those are happening throughout the world independent of the aerospace industry, and we're trying to leverage that. We do it on cars, we should be able to do it on airplanes eventually. The challenge is to take those batteries and have enough energy or power content and have them be lightweight. Where we are today, I think, is we're at the dawn of the age where we can start to see electric propulsion or hybrid electric propulsion. And you'll see it on smaller aircraft first before you see it on the large commercial transports. But that's what we're working towards. That's good for cleanliness, it's good for noise, it's good for energy efficiency. Has its challenges. That's why we're working on it, and that's why it's not being done today.
The idea behind this vehicle is to have its twin engines burn fuel when great power is needed, like at takeoff. But when the craft is in a cruise configuration, a switch can be made over to a battery electric mode to supplement or even replace power to the engines. If successful, this could reduce the amount of fuel burn by up to 70%. Another concept called turbo-electric propulsion is being studied here at the NASA Glenn Research Center. Here is NASA's Jerry Brown to explain.
There's not been electric airplanes except in very small size. And the reason is that electric motors and generators tend to be too heavy for flight. We're hoping to change that, and we're hoping to get a benefit from saving a whole lot of fuel in the process. The type of electric propulsion that we're talking about today is turbo-electric propulsion. We're going to keep the turbine engine because it's really good as far as a lot of power in a small power plant. And then we're going to use its power to drive a generator, send electricity to motors that drive fans that do the propulsion.
This concept will look very different from vehicles of today as well. Potential designs include 2 large turbine engines on the wingtips that will drive 2 large generators inside the body. The generators will in turn power a number of fans, providing the propulsion the aircraft needs to fly.
What we want to do here is we want to be able to break the turbine engine from the fan, and that gives the aircraft designer a lot of freedom. If he can move the turbine engine somewhere else in the airplane, that may itself have advantages. The engine and the fans don't have to turn at the same speed. You don't even have to have the same number of fans. And that's what we're really looking for, is we want to have an array of a whole bunch of fans, maybe 15 of them, say, and just 2 engines. You like to keep just 2 big engines because the big engine is much more efficient.
This idea is intriguing, but big changes need to be made to make it viable. One major challenge is the need to reduce the size of the generators, because the generators of today are way too big to fit on an aircraft. One idea that the NASA team is looking at is a way to remove the current type of copper windings in the generator and replace it with superconducting material. This change would allow the generators to shrink, making them viable to fit on future aircraft. we've seen so far, new aircraft designs are coming online that have the potential to greatly improve aircraft efficiency. Another of these revolutionary designs has come out of a joint MIT and NASA study. This unique design is called the double bubble and has the potential to reduce fuel burn by up to 70% as well.
So the MIT-8 double bubble design was something that's we've been working with MIT for a number of years on that. The idea there is to take some of the lift that you would normally get from the wings and try and move that to the fuselage. Another thing that's done to enable laminar flow on this vehicle is to reduce the sweep of the wings. It is easier to maintain laminar flow if the wings, instead of being swept back like a lot of modern commercial transports, are more sort of perpendicular to the side of the body of the plane. Another aspect of the D8 that we didn't really discuss is something you can see in these pictures behind you. You can see the picture on the right, which comes from CFD. The engines are what we call in the potted configuration. They're potted separately off to the side. The idea is we hope to get an airstream that's relatively untainted by what's happening over the airplane, a fresh airstream to go into that engine and create our propulsion. The image in the middle, on the other hand, the engines have been moved to inside that pie tail configuration. And by doing that, we actually get some benefits. If you can use the engines to refill that area of dead air behind the plane, you have a chance at being more efficient in terms of propulsion for that vehicle given a certain amount of fuel. We're trying to sort of push the envelope, see what is the maximum benefit that could be obtained by this kind of a configuration to understand what's really possible in terms of fuel savings.
Aiding much of the work is improved computational fluid dynamics and wind tunnel testing.
Right here in this building we have Pleiades supercomputer, which is one of the largest supercomputers in the US and in the world. It has 200,000 processors working on the problem if you use the whole machine on one problem. So it's a very large machine, and we need that very large machine because we need to do very big problems here at NASA. The aeronautics research director that we're using it for is to try and simulate the flow over these N+3 configurations. So in order to capture all the detail you'd see on a vehicle like this, including what's going on inside the combustors of the engines and things like that, you need to have a lot of grid points to resolve all the fluid motion inside those engines over the airplane, and having that many grid points to resolve all that physics in 3 dimensions creates very large computational grids that require very big machines to advance the equations that govern the fluid motion and get these CFD, computational fluid dynamics solutions that we use to make our assessments.
Aerodynamicists of today are able to model ideas on computers, which allows them to test many different configurations before a wind tunnel model is ever built. Once a design is agreed upon, a wind tunnel model can then be fabricated and tested. This process was used for the double bubble as well, but the wind tunnel test showed surprising results.
The good news is we've just completed the first test of this configuration in the Langley 14x22 wind tunnel at NASA Langley. And it showed even a greater reduction or a more fuel efficiency benefit to this technology than we had predicted on paper with our low-OR models. So we're trying to digest the experimental data that show this nice benefit in fuel efficiency from this configuration. At the same time, we're also using the supercomputer here at NASA Ames, the Pleiades supercomputer, to do computational fluid dynamics CFD runs of these same configurations and see if we can confirm that benefit on the computational side as well.
Testing will continue on the double bubble, and if the results hold, you may see this type of aircraft at an airport near you in the future. When testing aircraft, many different stages occurred. We have already mentioned CFD and wind tunnel testing, but another tool in testing future designs is to build a flying scale model. Although CFD and wind tunnel modeling is the mainstay, often test flights of these small, scaled-down versions of an aircraft offer some of the most dramatic results for researchers. That is the case with this aircraft, called the X-56. This aircraft is being used as a test bed to understand how different wing configurations work and how a unique idea called active control may be used in the future.
The whole concept behind the X-56 is that they've long known that very long wingspan vehicle is more efficient than short wingspan vehicles. Problem is though, when you get a very long wingspan, you start to get into issues with flutter modes that start to creep into the vehicle, so that the wing will go unstable and in extreme cases will rip off the vehicle. To get around that problem, you can use active flight controls to suppress those flutter modes. Active control is you put things like accelerometers within the wing, and as soon as you sense that the wing is starting to get into these flutter modes, you use the control surfaces behind the wing to damp that out. So the airplane, as it's flying, is continually fighting these modes and keeping the wing straight and stiff. Then you can build a lighter, longer wingspan vehicle that is more efficient. This vehicle, as funded by the Air Force, was built as a multi-utility technology test bed. They call it the MUT for short, and it is built to do a lot of different kind of testing in aeronautics. The wings are removable. You can put on a stiff wing, you can put on a flex wing, you could do a joined wing configuration. We can learn quite a bit from testing this kind of vehicle. Right now the focus is on flexible wing and active control of flexible wings, but in the future there are many experiments that can be done with this vehicle.
The research on the control of lightweight, flexible wings being performed today on the X-56 is key to enabling the long, thin, low-drag, and low-weight wings of tomorrow's N+3 configurations. Much is going into understanding what it will take to improve the already incredibly efficient aircraft of today into ultra-efficient vehicles of the future. Although we don't have all the answers yet, it's clear that NASA and its brilliant engineers and researchers are helping to lead the way to a safer and more efficient way to travel.
We are nowhere near the maximum that we can get out of this industry. And there is a lot of work to do, and that's what my team is doing. That's what we're doing within NASA, and I cannot wait for the future.